many components basically this dialogue act classification, intent detection, slot filling, dialogue manager, then natural language generation. So these are the different modules under dialogue system. So I will briefly discuss each of them in detail. So yeah, so basically this is the dialogue. Dialogue means that there are two parties and they are basically conversing. Like suppose there is an agent, hello, how can I help you? The person is saying my computer isn't working. So the agent is saying, hello, how can I help you? So there is a bot, or there is a chat bot. Basically it's called a chat bot or the conversational agent, and this conversational agent is basically conversing with the customer. So you can imagine a customer care representative is now replaced by a chatbot. So each company is having a customer care representative, and the customer care representative is now basically replaced by a chatbot, and this chatbot and the customer are basically chatting. Okay, they are discussing about some problems. So like here you can see, and then now the task of the chatbot is to collect the exact problem statement or the specifications of the problem statement by conversing with the user, and then basically the chatbot will try to provide a solution for the problem which the customer is facing. Okay, so this is the kind of scenario that we basically want to build. So we want to build a chatbot or a virtual agent which can easily converse with the customer. And maybe it's a task oriented setting. So the customer is having a particular task in mind, and the customer wants a solution for the particular task. So this task can be anything. This task can be booking a restaurant or booking a flight, okay, or asking the price of a particular flight. So it could be anything, or asking about the ground ground service of the particular flight. So it could be anything. So these are basically called the intent. That if suppose a customer is asking about the flight, inquiring about a particular flight given a source city and destination city, then this is basically called the flight information. But if the customer is asking for the price, then this is called the price information. So depending on the type of task, there is a specific intent involved. So our task basically here is to develop this kind of conversational agent which can try to solve a particular task of a user. Okay, so this is the basically the conversational agent. And now definition wise, what is a dialogue? So a dialogue is a formal discussion of a topic in speech or writing. So suppose I am now currently discussing about the dialogue systems. Okay, so if there are multiple parties, or there could be two parties or the multiple parties, and if they are discussing on a particular topic, then that is basically called a dialogue. So it is a formal discussion of a topic in speech or writing. It's a connected series of utterances, a text or conversation. So there are, it is a connected series of utterances. So I am talking to the other party. So there are multiple parties and there are two parties. It's an exchange of ideas or opinions on a particular issue with a view to reaching an amicable agreement. So there are different characteristics of a particular dialogue, like whose turn is it? So basically, when there are multiple parties, or if there are two parties also, then I suppose I am conversing with the other party. So we have to decide whose turn is it. So who is going to speak? What are the intentions? And how to reply back? So these are the different characteristics of a particular dialogue. And basically, we have to somehow understand this in order to build a chatbot or a dialogue agent. So, the dialogue agent has to first understand whose turn it is, whether this is agent's turn or whether the customer's turn. Accordingly, response will be generated. Then before giving the answer, before generating a response, the chatbot has to understand the intention of the user's utterance. So the user is saying something, and the chatbot has to understand what is the exact intention of the user. Because if the chatbot will not be able to understand the intention, the response will not be, context aware. So the response has to be generated, which will be context aware, and the context will come from the user's utterance. So first, the agent has to understand the user's intention, and then it has to generate the response accordingly. Then, there are different types of utterances. We will see that when suppose the user may ask some question, or user can give some statement, or user can give some greeting. So there are different types of utterances possible. So you can categorize the utterances into different categories. And now depending on the type of the utterance, the agent has to reply back. Basically, the agent has to generate a response. So basically, and it should be, somehow it should be correlated with the utterance which is said by the user. So this is the overall dialogue system. This, as I mentioned, the dialogue system is a component, is a basically overall package, and this is having many submodules. Okay, so the one submodule is called the natural language understanding. Another important submodule is called the dialogue management, and the third submodule is called the natural language generation. So natural language understanding, from the name itself you can easily understand. This deals with the understanding of the user's utterance. So like, for example, user is asking to book a restaurant. So user's utterance is, which restaurant can I book for 2 people for today? So if this is the user's utterance, now the agent has to extract information from this utterance. So here the date is today and the number of people is 2. So these are the relevant information those have to be extracted from this user's utterance. So this natural language understanding is having 3 tasks. So one is a dialogue act classification. So dialogue act classification is to understand the type of the utterance. For example, which restaurant can I book for 2 people for today? This is basically a question. Okay. So the dialogue act classification is a classification framework which will classify, which will basically output the category of the particular utterance. So this category could be question, greeting, statement, comment. I will show you in detail. There could be many possible categories, but the dialogue act classification is a classification framework. Mostly machine learning, deep learning techniques, classifiers are mostly used for developing the dialogue act classification. And it basically, detects the type of the utterance. For example, here it will detect that this is a question. Now the intent classification is basically to identify the communicative intention of the user. So for example, here the user's intention is booking a restaurant. So user wants to book a restaurant. So the intent classification will try to find out the intent as booking a restaurant. And then finally, there is a slot filling module. So this slot filling module will try to extract the relevant information. So for example, here the relevant information are date and the number of people equal to 2. So basically this slot filling module will try to extract the information from the user's utterance. So if the user is saying which restaurant can I book for 2 people for today, so the slots are date equal to today and number of people equal to 2. So these are the three different modules, and these 3 different modules come under natural language understanding. So finally, we are getting a state information. So the state is having 2 information: date equal to today and number of people equal to 2. So now this state is basically, and it's a request because the user is making a question. So now there is a dialogue manager component. So this dialogue manager is basically a reinforcement learning based agent. So this reinforcement learning based agent basically maps the state into action. Okay, there is a policy optimization. So it basically tries to optimize the policy, and then it basically given a particular state, it selects the optimal action. So for example, given the state that user wants to book a restaurant for 2 people for today, the next question, the next action is asking the category. So dialogue manager should ask about the category because without knowing the category, the dialogue manager cannot book the restaurant. So the dialogue manager is asking about the category. So accordingly, the response will be generated. So dialogue manager is asking about the category, and then there is a natural language generation module. So this natural language generation module accordingly will generate the response. So natural language generation is very difficult because it works like a human being. So it will generate the human-like responses. So in this NLG module, we can incorporate many concepts, like we can introduce the politeness, we can introduce the empathy. So we can introduce different types of characteristics to generate some like a polite responses, or to generate some empathetic responses. So this in natural language generation is again a kind of a big research field, and researchers are basically working in this particular area, and they are trying to introduce different types of human like features in the natural language generation model. So this is the overall dialogue systems. And now I will discuss each of these components one by one. So I will show you one of the tasks, basically one recent approach for solving these individual submodules. So let us start with the dialogue act classification. So as I mentioned that dialogue act classification is a first submodule. So the task of this dialogue act classification is to understand the, is basically to categorize the type of the utterance. So the user is saying something. So what is the type of the utterance? That is the task of the dialogue act classification. Here to identify the communicative intention of a speaker in a dialogue conversation classified into a predefined category. So, there are different types of utterances, and we need to identify the type of the utterance. So what kind of experience do you have then with the child care? So you can easily understand this is a type of a question. I think it is really, this is basically a statement. How about you? This is an open question. That's all right. This is an example of a understanding. So this way we can basically categorize the utterances into different, we are basically trying to identify the appropriate dialogue act of a particular utterance. So here we have utilized two data sets, SWBD and the trends. So this switchboard SWBD stands for the switchboard corpus. So this switchboard corpus is a very big corpus. It's already, this data set is available. So it is an informal corpus of human-human interactions. So there are 1,155 dialogue conversations amounting to more than 2 lakh utterances. Okay, so it's a two-party conversations. So there are two people are conversing with each other, and there are total 2 lakh utterances. And in this data set, each of these utterances are categorized into some dialogue into a particular class. So there are 42 such categories. Okay, there are 42 different types of dialogue acts. And then there is another data set which is called the trends. So it is a task-oriented corpus. SWBD is not a task-oriented. So SWBD is a kind of a chit-chat, like two people are simply conversing on a particular topic. Okay, but trends is a task-oriented corpus where maybe one customer is having a particular task in mind, and the other customer is trying to solve the particular task. So where an user collaborates with a planning assistant to accomplish some task involving manufacturing and shipping goods in a railroad freight system. So this is the task basically, and there is a planning assistant and there is a user, and they are conversing to each other, and they are trying to solve a particular task. So there are 98 dialogues amounting to about 7,000 utterances. So you can see there are 7,000 utterances and 98 dialogues. It is smaller compared to the SWBD. So let me discuss a particular work where we have developed a dialogue act classifier. So first of all, we need to understand the categories. So as I mentioned that dialogue act classification means we have to classify the utterance into a particular class. So there are in the original switchboard corpus, there are total 42 number of categories. But we cannot, it's a large corpus, and there are these 42 classifying 42 tags at a time is very difficult. So basically we have utilized some we have somehow grouped some of the classes, and we have generated some basically we have somehow marked some classes, and then we developed our own taxonomy. So as this switchboard tag set has fine-grained categories, not very useful for restricted domain applications. So we developed our own taxonomy that can divide the utterances into more generic classes. So basically, we developed a taxonomy, or which is basically a kind of tree-like structure. So we merged some of the fine-grained classes, and then we basically mapped to a coarse-grained class. Okay, so so that we should not deal with these 42 different categories. So flexible for modeling a chatbot. So basically here we have utilized these classes: question, acknowledgement, greeting general, statement, and the comment. So these are the 5 classes that we have basically utilized here. So we have basically somehow marked these 42 classes, and then we basically you utilize these 5 classes, course grain 5 classes. So these are our 5 classes. So question means you can easily understand this is a kind of a question contains utterances that represents any type of question. So like, who is Chris Manning? How are you? So these are the different types of questions. Then there is a greeting general. It involves greetings, goodbyes, and basic small talks, showing expression of gratitude towards listener. Okay, so greeting general involves greetings, goodbyes, and basic small talks, showing expression of gratitude towards listener, like good morning, good evening, good day. So these are the greeting general. Then there is an acknowledgement or CAT. This involves explicit affirmations, disagreement, or confusion from the user side, as well as the instances that indicate end of the conversations. So you know that some explicit affirmations or the disagreement or the confusion, like yeah, okay. So these are the different examples of acknowledgement of the CAT. Then there is some category called the command. So this involves asking the system to perform an action which may include display, search, generate, etc. So like pass the book, give me that bottle. So these are the different types of utterances which involve some command. So this is called the command. Then there is a statement of the information utterances that contains any piece of information that can be used to extract attributes. Like he is Austria right now. So here the Austria is an important slot. So some utterances from here you can easily extract some slot information. So these are the 5 categories that we are interested in. So we have basically categorized this fine grain categories into some coarse grain categories, and this is our taxonomy. So we have 5 classes: question, greeting general, acknowledgement, command, and the statement. So this is one example. You can see like agent suppose is saying hello, how may I help you? So this is a kind of a greeting. Then show me flights to Mumbai today. So this is a kind of example of a command. May I know the departure place? So this is a question. Oh, it's Bangalore. This is a statement because you can extract the information like Bangalore, which is an important slot. So you want to fly from Bangalore to Mumbai. It's a question. Yes, it's an acknowledgement. The flights are these at 2 p.m. and these at 10:30 p.m. So this is a kind of a statement. Thank you for the information. This is a greeting. So this is an example of a basically dialogue. So basically, yeah, you can see that how these 5 classes are occurring in a particular dialogue. So yeah, so this is a kind of a framework which can be utilized for dialogue act classification. So you can easily understand it's a very simple task. It's basically a classification problem. So given a particular utterance, you need to generate the corresponding category. It's a basically sentence level classification. So you need to consider the whole sentence and then you have to predict the category of the particular sentence. So somehow you have to represent the sentence into a vector representation. You know, there are different embedding techniques available. And by using those embedding techniques, we can easily convert the sentence into a vector form, keeping the semantic information intact. And then once we get the sentence vector, we can classify the sentence vector into any of these 5 categories. So yeah, so basically, you know, these are the steps. Data pre-processing and the taxonomy preparation, already I have mentioned that how we have prepared the taxonomy. So we basically merged these 42 fine grain categories and we basically generated the 5 coarse grain categories. You know how to reduce the complexity because handling these 42 categories is very difficult, and maybe there will be many minor classes as well, because amongst these 42 categories, some classes will be very minor, few instances will be there in a particular class. So it's very difficult to, you know, handle to deal with these 42 different categories. So that's why we have somehow created our own taxonomy where these 42 categories are merged into 5 coarse grain categories. So then we generated the word vectors. So, you know, for basically, we are first identifying the word vectors. A sentence may have multiple words. We are generating the word vectors. and then we are concatenating these word vectors, or we are calculating the average of the word vectors to find out the sentence vector. Now, there are different strategies. So in one methodology, you know that in a methodology one, which is the very simpler one. So here what we are doing, we are manually extracted some features. So I will discuss about those. So we have manually extracted some features, like we have manually extracted, you know, that if it is a question, then the it will start with some WH words: what, where, who, or how. So these are the some, you know, whenever we are asking some question, it has to be, it will start with WH or the W of the how, these words. So we are seeing whether those words are the first word of a sentence or not. Accordingly, there will be a binary feature. So if the first word is starting with the WH, or it is a how, etc., then we are making a binary, you know, the corresponding binary feature will become 1, otherwise it will become 0. So basically this way we are manually extracting some features, or suppose at the end if there is a question mark, then also we are introducing a binary feature, and this question mark will help us in understanding that this is a question. So yeah, so basically we are extracting all the features, and then you know, there is a CRF, conditional random field, which is a machine learning classifier. So we are using CRF as a classification algorithm, and with all these features we are training the CRF, and then we are predicting the appropriate dialogue act. Then in the second task, we are basically, what we are doing, we are not only from these manually extracted features, we are selecting some subset of features. By using some feature selection technique, we are selecting a subset of features. You know that there are different feature selection techniques available, like forward selection, backward selection. So by using these feature selection techniques, we can select a subset of features, and then we can also add the word vectors. Like here we have generated the vector representations of the words. Those word vectors are added, and then we are passing them through the conditional random field. So CRF is the classifier, and we are predicting the dialogue act. So this is the methodology 2. And then there is a third methodology. In the third case, what we are doing, we are basically applying clustering of the vectors. So you know, there are we are having the basically we are clustering the word vectors. So if some words are semantically similar, then they will form a particular cluster. So instead of using the exact vector representation of a particular word, we are simply using the cluster number to denote that particular word. Okay, so basically here first we are clustering the word vectors. So if some words are semantically similar, then they are in a single cluster, and we are replacing the word with the corresponding cluster ID. Okay, we are not only using the appropriate exact vector, but we are replacing the word by the index of the cluster, or the cluster ID, and that will be our new feature vector. And then we are using this and we are using this in the CRF framework, and we are identifying the dialogue act. So this is the methodology 1, which I mentioned earlier. So in methodology 1, we are extracting some manual features. Okay, we have done some feature engineering. Manually, we have extracted some features, like some features are lemma form of the word, which is basically the root form of the word. Okay, you know, a word is having some prefixes and suffixes. So we are discarding those prefixes and suffixes, and we are generating the lemma form of the word. Then we are also generating the lemma bigrams. So basically, maybe consecutive 2 words lemmas we are considering. We are not only considering the lemma of the current word, but lemma of the consecutive 2 words. Then part of speech is also sometimes important. So part of speech, you know, that we can understand whether it is a noun or a verb or adverb or adjective. So we are also computing we are also determining the part of speech of individual words, and then those are used as features, and also their bigrams. Then speaker is one important feature, like who is talking. So whether it is the user's turn or the agent's turn. So the speaker information is also used as a feature. Then there are some class specific features, like, you know, question. For example, I mentioned the presence of 5 W1 words: what, where, when, which, who, how, etc., or question mark. So whether the first word is starting with the WH word or not. So like whether we are starting with this WH word with or how, etc., and whether this is ending with the question mark or not. Then greeting general presence of sorry, thank you, hello, hi, etc. So and then cat, for cat we are seeing whether there is a presence of who, okay, yes, no, etc. So these are some class specific features, and we are seeing whether these words are present in the utterance or not. So if these words are present, then we are marking, we are basically, there is a binary feature. So for we are seeing whether these WH words are present, or it is starting with how, or at the end there is a question mark. Accordingly, there is a binary feature vector. For greeting also, we are searching with the presence of this sorry, thank you, hello, hi, etc. And if these words are present, then we are making a binary feature vector. So this way we are generating some binary feature vectors. So to improve the ablation study, to improve the accuracy and identify important and contributing features. So basically, you know that we have done some feature selection. So we what we have done, so maybe all the features are not important. So what we are doing, we are basically identifying the important features. So we have done in a forward direction. So at a time, we are selecting only a single feature. So initially, we are starting with a single feature, and then we are adding some other features in the set, and then we are checking the quality of the particular feature subset. So maybe initially we start with only part of speech tag, and then we add the speaker information. Then we add some binary features. So that way, in a forward direction, initially we start with a single feature, and then we keep on adding some other features in the set, and that way we are generating some feature subset, and we are using the CRF classifier with this feature subset to find out the accuracy. So the difference in the accuracies is used as an estimate of the importance of the feature. Okay, the difference in the accuracies. Yes.
Ma'am, I have one doubt, ma'am.
Yeah, please.
How many features do we need for any proper study for each vector?
No, it basically depends, it depends on the problem statement. Like, sometimes some features are, for example, here you can see that if you want to identify the question class, then maybe this binary feature, which is checking whether the 5WH words are present or not. So that is sufficient, no? Because it's very important feature. So if the sentence is starting with the WH words, or it is ending with the question mark, then you can surely say that it is a question. So, it depends on the complexity of the problem. In some cases, classes are very easy to identify. In that case, you only need one or two features. But in some cases, there is overlapping between the classes. And there you need to have more number of features. It depends on the complexity of your problem statement, or the type of classification problem that you are trying to solve.
Okay, ma'am. One more doubt, ma'am. What do you mean when you say lemma? Like, we have heard about pumping lemma in our. That's not different from this, right? That's different.
Yeah. So here lemma means a root word. Okay. So like mine. So or maybe if you are saying like Sripornas. Okay, so Sriporna's root word is basically the Sriporna. So or goes, the root word of the goes is go. Okay, so you are basically removing the prefixes and the suffixes, and we are just finding out the root word from which it was generated. Okay, so like went, if there is a went or goes, then the root word is basically the go. So we are just trying to find out the root word. We are simply removing the prefixes and the suffixes, which are very common in our Indian setting, in English also. So we are simply removing those prefixes and suffixes, and then we are just finding out the root word from which it got generated.
Okay, ma'am. Thank you.
Yeah. Okay. So Rohit, I didn't see that question. There is a question. So my ma'am, question can be asked in form of statement like, I want to know about trains from Mumbai to Delhi. Then how presence of WH features will take care of the same. Yeah. Yes, yes. So basically, Rohit, if you are asking, I want to know about trains from Mumbai to Delhi, then this is a, yeah. So it's again a question, but it's more like a statement because the user is here. There are some important information also present. Like you can see the source city and the destination city are mentioned by the user. So it will be tagged as a statement. And then, I mentioned about the other modules, like we have this intent detection and the slot filling module. So the intent detection will automatically understand that the user is trying to understand about the trains. He is basically a user wanted to book a train. So we are not only relying on the dialogue act classification. We are also, there are some other sub modules as I discussed earlier. We have the intent detection module, we have the slot filling module. So the intent detection will try to identify the intent of the user. Okay. So here, for example, the intent is booking a train, and the Mumbai and Delhi are the slots because these are the source city and the destination city. So yes, so basically, yeah. So yeah, I understand this is a type of a question only. So the if you are using the 5 WH words, then you will not be able to understand. That's why basically you can see that we are not only relying on a single feature, but we have several other features as well. Okay. And especially if you are using these word vectors, like as I mentioned that there is one approach where we are using the word vectors. So these word vectors will also help us in understanding the actual intent of the user. And finally, we have this intent detection module. So this intent detection module will help us also in understanding the user intention. So Rohit, am I making sense? Okay, yeah. Yes, so yeah, so these are the thing. Yes, as I mentioned that we did a ablation study because all the features are not important. So initially we start with a small set of features, and then we keep on adding some new features in the set, and then we are evaluating the classifier. So the best performing features are taken and rest of the features are dropped to reduce the complexity. So yeah, so this was the approach 1. In approach 2, as I mentioned that here we are using the word embeddings. So each word can be mapped, can be for a particular word we can generate the embedding, and this embedding is basically a semantic representation of a particular word. So this what-to-vec models or the globe models. So by using this what-to-vec models or the globe models, we can easily generate the embedding of a particular word. So yeah, so basically these embeddings are nothing but a vector representation of a particular word where in a semantic space. So we are basically mapping the word in a semantic space, and then we are representing the word in a numeric format, which is a vector numeric vector basically. And in the semantic space, you know that if you see the distance between boy and girl, that will be very much similar to distance between man and woman. Okay, so yeah, so basically we are finding out the embeddings of the words, and those embeddings will be used as the feature vectors. And also we are concatenating this, we are basically also adding the features which are obtained from this ablation study. So this is called the ablation study of the features. Here we have tried to identify the importance of the individual features, and then those features are added with the word embeddings. So this way we are generating a long feature vector, and that is used for training the CRF model. So CRF is a machine learning classifier. So we are using CRF as a classification framework here. So pre-trained Google News word embeddings of dimension 300 is used. So in the third methodology, you know that we have a classifier CRF. We are somehow clustered the, we are basically clustering the words or word vectors. So each word is having a vector representation, and now we are applying the clustering of these words. So, and then each word will be replaced by the cluster ID. So we are applying clustering of the word embeddings. So as a result of that, the semantically similar words will form a particular cluster. And now each word will be replaced by the corresponding cluster ID. So best performing features obtained from the ablation study. So lemma, unigram, bigram, part of speech, unigram, bigram, etc. So this is our methodology 3. So here we are first applying clustering on the word embeddings. We are generating some clusters, and then by clustering, basically we are grouping the words which are semantically similar. And basically whose meanings are basically similar, and then each word is replaced by the cluster ID. Okay, and this and not only this feature, we are also having other features. So here we did a ablation study, and by after application of the ablation study, we found out a good set of good features. So those features are also added with this cluster ID, and then we are training the CRF. So here is a representation. So you can see, like, suppose the user's utterance is what? Show me flights from Denver to Baltimore. So these are the unique words in the utterances. Show me flights from Denver to Baltimore. So these are the words. So now first we are generating the word vectors. So we have this word to vec, or we can use the globe embedding as well. So by using the word to vec or the globe embedding, we are generating the word vector of a particular word. So this is the vector representation of show, vector representation of me, vector representation of flights, etc. So now we are applying the K-means algorithm, and by applying the K-means algorithm, we are grouping the similar words. Like all the city names are grouped together, all the the prepositions all the group together. So this way, semantically the words which are semantically similar are grouped together. And then now what we are doing, we are replacing the word by the cluster ID. For example, show is now part of maybe cluster number 3. So we are replacing show by G_3, me G_29. So this way we are replacing the word by the corresponding cluster ID, and then we are generating a basically a vector. So this is our vector representation, and this vector basically this vector denotes a particular particular utterance. So this is so basically and in methodology 4, so these are all our machine learning based approaches. So in machine learning based approaches, we have to think of the manual feature engineering. So we have manually created the feature vectors. But now there are some also deep learning based approaches. So in the deep learning based approaches, we are using some deep learning classifiers. Yeah, so Joby, very good question. So yeah, we can also use any other classifier as well. So the motivation of using CRF is that it is a sequence labeling. CRF is based for the sequence labeling problem. So here also the sequence matters. Like suppose if previously user has asked a question, so then maybe in the basically the agent will provide an answer. So this answer will be of type question of type statement. So or maybe if suppose the user has greeted the agent, then now the agent will also greet the user. So there is a somehow there is a sequence matters. So it's a CRF is very good if it is a sequence labeling problem, like the output of the current utterance depends on the output of the previous few utterances. Yes. Joby, very yeah. We can also use the LSTM. Yes, we can also use the LSTM or the transformer classifiers. Yeah. Then on the same logic, we can use them. But yes, so either you can visualize this as a sequence labeling task, or you can also use some other classifiers like support vector machine, etc. But yes, so as we decided to use CRF because we thought that this is a sequence labeling task. Yeah, so in our methodology 4, we use some deep learning based model. So here, we have used the CNN to extract the features. So CNN is used with different filter sizes, filter size equal to 3, filter sizes of 3, 4, 5, etc. So yeah, to the baseline, we have used the LSTM also. And first we are extracting, CNN is very much capable of extracting the character level features. So CNN is very much useful in extracting the character level features. And so that's why basically we are using the CNN. And finally, we are also adding the features like part of speech and the cluster IDs, which are augmented with the system. So this is our proposed approach. So you can see that we have the word embedding. We are applying the CNN with different filter sizes. On the word embedding, we are determining different character level features. Then we are concatenating these character level features. Similarly, we are having this part of speech and the cluster embedding, and we are passing through the CNN layer, and then we are extracting some features from the part of speech, etc. And all those are concatenated together, and then there is a RNN unit, and finally there is a dense layer for the classification. Yeah. Yes, please go ahead. Any question? Okay, so this is a kind of a approach which can also be used for dialogue classification if you want to go with the deep learning. So these are some of the results. Like if you are using all features, so all features means all these features which I mentioned here: lemma diagrams, part of speech diagrams, speaker information, class specific features. So if you are concatenating all these features and then you are classifying using CRF, then we are getting the accuracy of 7. You can see that there are 2 tag sets. In the originally there are 42 tags in the switchboard corpus, and we basically merge these 42 tags into 5 tags, as I mentioned earlier, that we are basically generating a coarse grain tag set. So that is our proposed tag set. So with all features, the accuracy was 72.50, but with our proposed tag set, we are getting 90.87. Similarly, F1 score was 48.08, but now with the proposed tag set, we are getting 76.17. Now here again, you can see that all features are giving as the accuracy of 72.50, and with the proposed tag set, we are getting 90.87 accuracy. But with the base features, like we have done an ablation study, as I mentioned you, we have applied the forward feature selection, and by using the forward feature selection, we are selecting the important features. And by using this methodology, we are getting the accuracy of 72.48, and with the proposed tag set, we are getting 90.88. So you can easily understand that identifying 42 different tags is very difficult, and sometimes there is overlap between the tags as also. Like as we are dealing with 42 tags, there are some minor classes, some major classes. Class distributions are not uniform. So that's why the accuracy is not very high. F1 score is only 48%. But when we are merging these 42 tags into our proposed 5 tags, then the F1 score goes up to 76%. Yeah, so this is the methodology 2. So here, what we have done, that we have, we are using the word embeddings. Only by using the word embeddings, we are getting with our the proposed tag set, we are getting 71.55 for score, and with the original 42 tags, we are getting 41.35%. And when we are adding the other features with the word embeddings, then you can see that result is 46% with the original tag set, 75% with our proposed tag set. Yes, so I think you are very correct, Zobi. So basically, you can use the PCA as well. We have not used PCA because the PCA, the problem is that PCA is a transformation. No, basically it is a feature selection technique only, but it basically projects the original vector into a lower dimensional vector. So this in a lower dimensional space. So in a lower dimensional space, it is very difficult to interpret the features, because it will transform the original feature vector into a lower dimensional space. So here, for example, we have the meaning of individual features. So we have the part of speech, we have the lemma, we have the different binary features. So, but if you use PCA, then it will be projected in a lower dimensional space, but you will not be able to interpret the meaning of those features. So that's why we have not applied PCA. We have used this forward feature selection of the backward feature selection, so that you can, we can easily understand that which feature we are going to select or which feature we are going to drop. So, and that was the motivation of this forward and the feature backward feature selection. Yes. So yeah, these are some results with the methodology 3. So you know that yeah, recursive features addition. Yes, it's basically forward feature selection or the backward feature selection. We started with a small set, then we kept on adding some one feature at a time, and we are checking the quality of this feature subset. So it's a very simple feature selection technique, which is called basically the forward feature selection. So that we have applied. Yeah, so in methodology 3, you know that we apply the k-means clustering. As I mentioned, that we are applying clustering on the word embeddings, and we are grouping the words into some homogeneous clusters. And then from the we are replacing the word by the cluster ID. So yeah, we are having the cluster IDs and also all the base set of features. And these are the results with the original switchboard corpus. We are getting the F1 score of 47%. With the proposed tax set, we are getting 76.4443. So, and this is the methodology 4. We are using the deep learning based techniques. We are using CNN, RNN, and the additional features. And you can see the results are with the part of speech, we are getting 90.26. With the cluster, we are getting the 91.13. And these are some error analysis. You can see whenever you know in NLP, you need to do the error analysis, because your obviously your system is not 100% accurate. There are some misclassifications. So you need to understand what are the possible reasons for errors. So what are the possible reasons for errors? For example, you can see, can you tell me the way to Patna? So here the predicted category is command, but the originally this is a question. So basically, can you have two literal meaning? So can you tell me the way to Patna? So here you can see that here this can you have two literal meaning. It could be a question, it could be a command. So originally it is a question, but our system is predicting as a command. So I am going to Lucknow, book me a hotel there. So here again, what you mentioned, okay, that I think somebody already chatted with me that this kind of say utterances are basically command type. But as we are not starting with a verb, because what would be the easiest way to identify the command type of utterances is that utterances will start with a verb. But here utterance is not starting with a verb. So basically we are predicting this as information, but originally this is a command. So utterances are not explicitly command types. Then okay, I will also come tomorrow morning. So this is here the predicted is cat, and the original is basically the information. So cat has much occurrence of words like okay, yeah, etc. No, it's not possible. So here the predicted is information and the original is basically cat. So it's a replying to a question. Okay, so basically these are some error analysis. So okay, you can see that here there, because of the presence of some other patterns, our classifier is not able to correctly identify them. So yes, so if there is any question from this, you please ask me. Otherwise, because now I would like to discuss a new topic, which is also related to dialogue act classification, but I will show you how multimodal information can help in dialogue act classification. So any question till now, till this point? Okay, so then let us discuss about a new concept, new topic, which is called the multimodal dialogue act classification. Okay, so you know that what do you mean by multimodality? Already I introduced in the last class when I discussed about the multimodal summarization. So I mentioned to you that multimodal information processing means that you are not only relying on a single source of information, but you are relying on multiple sources of information. For example, you can have image and text both. So you can extract features from images, you can extract features from text, and then you can even concatenate them together, and then you can process this feature vector together. So if you are collecting information from multiple sources, then this is called the multimodal information processing. And the multimodal information processing is nowadays very common, because everywhere, whenever we are writing in social media or in the newspapers also, you can see that we are not only writing the text, but we are also uploading images, we are uploading videos, etc. So multimodal information is now very much available in social media, news reports, etc. So basically, sometimes because this sometimes this multimodal sources are complementary to each other. I already discussed in the last class that sometimes some concepts are very difficult to express using text, but you can simply show an image to basically, and this image can give you better information to understand the concept. So like how a piano looks like, so it's very difficult to describe in text, but you can simply show an image of the piano so that the readers can easily understand how a piano looks like. Similarly, but there are some concepts like freedom, love, affection, etc. These are very difficult to be expressed using images. So you can better express them by using text. So text and images are somehow complementary to each other. And that's why we are nowadays talking about the multimodal information processing, where rather than relying on a single source of information, we are relying on information collected from multiple sources. Okay, so here also we will show you that suppose when you have to identify the appropriate category of the utterance, if we have the speech signal, like if we also see the user's facial expressions, or we can also see the tone of the user, and not and apart from the textual representation of the utterance, then we can correctly predict what is the appropriate dialogue act. Okay, so this is the motivation that now we want to solve the dialogue act classification in a multimodal setting, where we till now I discussed about some approaches where we only have the textual representation of the utterance. But now we will be considering not only textual representation of the utterance, but we will also consider the tone information, the video information. From the videos, we will try to identify the facial expressions, eye movements, etc., and also the emotion of the speaker. And then by using all these modalities, we would like to correctly identify the appropriate dialogue act. Okay, so this is the motivation of solving this as a multimodal classification problem. So the idea is very simple, that the non-verbal features, the change of tone, facial expressions, can help us in better understanding the dialogue act. Like okay, sure, yeah, right. These utterances can have two different meanings. Either those could be mentioned in a positive way or in a negative way. So these utterances can be considered as agreement or the disagreement. So if they imply sarcastically, then those are disagreement, and if they imply normally, then those are basically the agreement. So mostly in expressive DAs such as greeting, thanking, apologizing, etc., speaker's emotion can assist in recognizing communicative intention. So you can understand that especially in greeting, thanking, apologizing, etc., there are two different meanings. Either there is a positive meaning, either user can mention them sarcastically or maybe in a positive way. So in order to correctly identify the dialogue act, we need to understand the speaker's emotion as well. So if the speaker is happy and saying okay, sure, then this is a kind of agreement. But suppose the speaker is very angry and speaker is saying okay, sure, then this is an example of a disagreement. So basically here, our hypothesis is that we'll be using the multimodal information. We'll not only relying on the textual representation of the utterances, but we'll also consider the other modalities like the image and the basically the audios and the videos. And also we'll consider the emotional state of the speaker. So the idea is that the emotional state of the speaker has a substantial effect on the pragmatic content. So so basically now I will discuss about a not a complex, but it's very sophisticated deep learning architecture, and it's basically a multitask architecture. So here we will be solving two tasks simultaneously. Dialogue act classification is our primary task, and the emotion detection from the speaker is the auxiliary task. So because multitask algorithms are nowadays very much popular in natural language processing, because in natural language processing some tasks are interconnected. Like for example, sentiment and emotion, these are some interconnected tasks. So if the sentiment is, if you can correctly identify the sentiment, then it can help you in correct identification of emotion. Okay, if the sentiment is positive, then the emotion cannot be anger or the disgust. The emotion would be happy, etc. So basically, sentiment and emotion are two interrelated tasks, and it has been shown in the literature that if we can try to solve these two tasks simultaneously, then one task will help in correct identification of the other task. So these multitask algorithms are nowadays very popular in natural language processing. And here basically we have developed a multitask-based approach where our main task is the dialogue act classification. Okay, that is to identify the category of the utterance. But it will be done in a multimodal setup where we will not only consider the textual representation of the utterance, but we will also consider the the audios and the videos. So audios will give us the frequency or the tone information, and the video will basically help us in understanding the facial expressions, eye movements, etc. So yes, so we will be proposing a attention-based multitask, multimodal deep neural network. I will discuss in detail. And here, as I mentioned, there are two tasks which will be simultaneously solved. The primary task is the dialogue classification, and the emotion recognition is the auxiliary task. So first of all, in natural language processing, whenever you will do some research in natural language processing, you have to first identify the data set. Because suppose you are developing some model, you have to evaluate your model on a data set. And if the data set is not available, in that case, you may sometimes have to create your own data set. Okay, so when we started this particular research, there was no data set for multimodal dialogue classification. So you have seen the switchboard or the ATIS data set. So the switchboard and the ATIS data set are the text-based corpus. So only text or utterances were present in those data sets. But now we are now interested in the multimodal. So we also need to have videos and the audios in the data set. So basically, that's why we created our own data set, which is called the EMOTIDA. So this is a multimodal emotion DA. So in this data set, there are three modalities: audio, video, and text. And each of the utterance is having two tags. One is for the dialogue act, and the second is for the emotion. Okay, so this EMOTIDA data set is having some high quality annotations of dialogue acts, including emotionally aided cues for facilitating research in multimodal DSC and lead to a novel subtask, emotion-aware DSC. So we have a task dialogue act classification, and basically here we are using the emotion recognition as the auxiliary task, and we are using three modalities: audio, video, and text. And we have shown that how multimodality helps in improving the accuracy. So like we have shown that if you are only relying on textual information or only audio information or the video information, so and if you are combining these three information together, then this multimodality performs better compared to the unimodal systems, as well as the multitasking performs better than the single task systems. So yes, this is regarding the data set creation. So when we started, as I mentioned, there was no existing data set in a multimodal setting for the dialogue act classification. So we searched a lot, and then we found out two data sets. One is called the IMOCAP and the MELD. So these two data sets are useful for the multimodal emotion recognition. Okay, people have in recent years, researchers have also started working on multimodal emotion or the multimodal sentiment analysis. So very similar to our dialogue classification, they're also checking the tone information or the facial expressions or the eye movements to identify the actual emotion of the speaker. Okay, so this IMOCAP and the MELD are two data sets available in multimodal setting, and these data sets are annotated with the emotion tags. So, there are basically now we basically annotated this data set with the manually, we have annotated this data utterances with the dialogue acts as well. So these data sets are not annotated for their corresponding dialogue act, So, in the switchboard corpus, there are 42 different categories I have already discussed, but we selected 12 most occurring categories, okay? We have selected 12 most commonly occurring tags, and these 12 most commonly occurring dialogue act tags are greeting, question, answer, statement opinion, statement non-opinion, apology, comment, agreement, disagreement, acknowledgement, back channel, and the others. So these are the 12 categories, and we annotate each of the utterance with any of these 12 categories. And to remove the discrepancy in the number of emotion tags for IMO cap and mailed. So this IMO cap and mailed, the sources are different, and there were some discrepancies in the emotion categories as well. But we want to combine these two data sets together, because we really want to generate a big data set, large data set for this multimodal dialogue act classification. To remove the discrepancy in the number of emotion tags for IMO cap and mail dataset, the joy tag of the mail dataset was mapped to happy tag of IMO cap to finally settle all 10 emotion tags from IMO cap for the Emotida dataset. So this is our final dataset. So Emotida is having 1341 dyadic and multi-party conversations, resulting in a total of 19,365 utterances. And as I mentioned, each utterance is having 3 modalities: audio, video, and the text. Okay. And each utterance is basically having 2 classes, one for the dialogue act, another for the emotion. So like adders don't snap this string. So here the dialogue act is the disagreement, emotion is anger. Come on, pick up, pick up. So here dialogue act is basically comment, and the emotion is basically fear. That's very amusing indeed. So here the dialogue act is disagreement and the emotion is anger. So this way that we are each utterance is having 3 modalities. We have the audio signal for the corresponding videos, and also the textual representation of the utterances. And we have 2 classes, dialogue act and the emotion class. So in our data set, we have this distribution. IMO cap is 48% utterances are coming from the IMO cap data set, 52% are coming from the mail data set, and this is the speaker distribution. So you can see these are the distribution of different emotion classes. So we have neutral, sadness, anger, fear, happy, surprise, disgust, and frustrated. So frustrated is only present in the IMO cap, not in mailed. Then disgust is mostly present in mailed, not in IMO cap. Surprise is also present in mailed, not in IMO cap. But anger is equally present. Fear is again present in mail, not in IMO cap. Happy is equally present. Assets. Sadness is mostly present in the sadness is mostly present in the IMO cap. So this is distribution of different labels in these 2 data sets. Similarly, these are the distribution of the dialogue act. So we have the statement, question, answer, greeting, apology, comment, agreement, disagreement, others, others. Then this acknowledgement, back channel, and the acknowledgement, back channel, and the others. So these are the 12 categories, and these are the distributions of categories in these 2 data sets. You can see that greeting is mostly present in mailed, but agreement is equally present in mail and IMO cap. So yes, so these are the distribution of the dialogue act labels. And why the emotion is important, because you can see that if you see some utterances like I can't leave it, you go the hole in my dingy floor. Here that if you easily, if you know the emotion, here the emotion is anger, and if you know that the emotion is anger, then we can easily understand this is a disagreement type. Okay, so emotion basically helps us in understanding the appropriate dialogue act. Well, I appreciate you coming over and talking to me. I mean, it definitely helps. So here also you can see that emotion is basically, that if you know the emotion is sad, then you can easily understand this is an example of acknowledgement. So this example illustrates the importance of having emotional information while deciding the DA of an utterance. So as we already know the emotion, so this emotion information basically helps us in understanding the appropriate dialogue act. So the presence of emotion in the dataset caters the models with the ability to use additional information while reasoning about the dialogue act. So this example illustrates how emotion, if you know the emotion, then this emotion basically helps us in understanding the appropriate dialogue act. And these examples basically illustrate how multimodality is helping. So for example, if you see, that's very amusing indeed. So here, from the text, it looks like this is a kind of a agreement. But if you see the audio and the video tones, so audio is a sarcastic tone and the video is a slight anger. So if you consider the audio and the video signals, then you can easily understand that this is no longer a agreement, but this is a kind of a disagreement only. Okay, so basically you can see that or the multimodal information basically help us in better understanding the corresponding utterance. Fine, then you tell Roger because he was really looking forward to this. Here text suggests agreement or the opinion, but if you see the audio and the video, audio is commanding tone and the video is furious, then you can easily understand that this is not no longer a agreement, but you know that this is an example of a disagreement only. So in both the examples, there exists inconsistency between the modalities, which acts as a strong indicator that the multimodal information is very much important in giving us additional cues for identifying the dialogue act. So basically, this multimodal information are complementary to each other, and as a result, we are better able to identify the dialogue act. So now, this was about the data set. So now about the proposed approach. So how we are developing the multitask, multimodal approach for solving this dialogue act classification, where emotion recognition is basically our auxiliary task. So you know that as there are three modalities, we have to extract feature vectors from individual modalities. So we have the textual modality, we have the audio modality, we have the video modality. So we need to first extract feature vectors from these individual modalities. So for the textual features, we are using the, we have the say utterances, which are called the transcriptions or transcripts. So we are using the globe embedding. So we are passing this, transcripts of the utterances through the globe embedding, and we are generating the word embeddings for the individual words which are in the utterance, and then we are averaging them. So if the utterance is having 10 words, we are taking the average of these 10 words to get a final utterance representation. Now for the audio features, to elicit features from the audio, we are using the OpenSmile, which is an open source software. So this OpenSmile is an existing tool. So here we have not developed our own model for extracting the audio features, but we are using the pre-trained models. So OpenSmile is already a tool available. So we just give the input of the OpenSmile is the audio clip, and then this OpenSmile will provide us the feature vector. So features are again concurrent. Basically, there is a window of Basically, we are dividing this audio clips into different small segments. A segment is, or it is a window-based approach. So for each window, we are passing the signal to the OpenSmile. OpenSmile is giving us a vector representation, and then we are calculating the average of these vector representations to get the audio features. So features are concatenated together to form a 256-dimensional representation for each window. The final audio representation of each utterance is obtained by concatenating the feature vector for every window. Then we also have the video features. So for the video features, what we are doing, we are basically using the we are basically finding out the keyframes. Okay, because for the videos we are first finding out the keyframes, and then keyframes are considered as the images, and we are extracting the features from these images. To basically we use the ImageNet pre-trained ResNet 152 image classification model. So there are keyframes are passed through this ImageNet to get the feature vectors, and then we are concatenating them together, or we are taking the average of these feature vectors. So these are basically we are generating the video embedding, text embedding, and the audio embedding. And now for the textual modality, we are having 3 LSTMs. So 3 individual BiLSTMs are used to learn different semantic dependency features. So one BiLSTM is learning the dialogue act classification features tuned in accordance with the emotion features. Okay, so one biolestem is learning the dialogue act classification features tuned in accordance with the emotion features. Second biolestem learns features for the emotion recognition task regulated by the learning of the DA features. And the third biolestem learns private features for the task DAC not influenced by the emotions. So there are three different biolestems. We also have the audio features and the video features. And then we have the Q, K, and V values. So this Q, K, and the V are used for the attentions. So you know that is similar to this 20. So there is a paper already. So we are also putting some attention. So attention is basically, given the video signals, we are putting attention or the emphasis on some part of the text. Again, is given the audio signals, we are putting emphasis on a part of the text. So this way we are putting the attention. So attentions are computed by using this Q, K, and V values. We have three different types of attentions.
Ma'am?
Yes. Yeah.
One doubt, ma'am. How would you train the data set for this case where we have a set of images and we have to identify which image is matching with which image? So we would make batches and do it, or we should do it like individually? How do we do that?
So in as I mentioned, in our case, this synchronization is not required. Okay. So in our case, suppose this is the utterance. Okay. That's very amusing indeed. So for this utterance, we already have a audio signal and a video, small video. So a video where speaker is uttering this utterance. Okay. So we already have this mapping that this utterance is said in this video, in this audio only. So now you do not have to map. Okay. So now you only have to consider that window in the audio side and those keyframes in the video side. So in the video, we are identifying the key frames from the video because it's maybe a 2 second or 3 second video. From this 3 second or 5 second video, we are simply identifying some key frames, and then these key frames are considered as the images, and we are extracting the image feature vectors. Similarly, it's a window. It's an audio signal of 5 seconds, and we are applying the open smile to get the audio features. And the textual representation we have, utterance representation we have. So we are using this globe embedding to get the utterance representation. So am I making sense? So basically you do not have to map because already in the dataset is created like this. So it's already given that see this utterance is said in this interval. So you have the audio and the video of that particular interval.
So, ma'am, these intervals are made. How are they created?
Oh, yeah. So this IMO cap and the mail, these two data sets are basically from some popular TV dramas. So this from the OTT platforms and from the popular dramas, they have basically they have extracted these audios and the videos.
Okay, ma'am. Okay, understood.
Spandan, are you getting me? So basically,
yes,
suppose I am talking now with you. So we are conversing. So maybe there is one utterance from my side. So the corresponding video is captured. So they've just identified that particular portion of the video where this utterance is uttered. And that is a sample. Okay. This utterance, the corresponding video clip is a sample.
Okay.
Yeah. So So basically, yes. So this is the proposed methodology. So we applied attentions just to focus on a part of the text because maybe the entire utterance is not important. You need to focus on a part of the utterance, which is and this portion can be easily identified based on the available audio and the video information. Okay, so we are putting the self attention, intermodal attention, intertask attention, because there are two tasks, emotion and the dialogue classification. So based on the emotion task, we can focus on a part of the utterance. So these are the different attentions that we have used. And finally, it's a complicated model. And finally, we are getting a final representation for the dialogue act and final representation for the emotion. Okay, by applying these attentions are nothing but the weights. When basically we are having three modalities, so you have to consider all these three feature vectors, and now we are putting some weights on these three feature vectors, and then we are computing the weighted average of the feature vectors, and that gives us a single feature vector for the dialogue act and one single feature vector for the emotion recognition. So, and then finally there is a classification layer, and this classification layer is there are two separate path. One path is for the dialogue act classification, another for the emotion recognition. So in the dialogue act classification, as I mentioned, there are 12 tags, and the emotion we have the 7 tags. So we are getting the corresponding outputs, and error is basically the error is calculated in both side, in the dialogue act side as well as the emotion side, and though we are basically combining the errors together, and then that is back propagated to train the network. Okay, so we are putting more emphasis on the dialogue act side because this is our primary task. So this error, while we are calculating the loss or the error, we are putting more emphasis on the dialogue act side rather than the emotion side. So, so this is now the proposed architecture. So errors computed from each of these channels are backpropagated jointly to successive prior layers of the model to learn joint features of both the tasks. So basically, our task we are training this model so that that the system can easily understand what will be attribution weights and how to extract efficiently the feature vectors. So we perform experiments on different settings. In this emoted data set, which is a combination of IMOCAP and mailed, there are some dyadic conversations. Only two customers are talking to each other, or there is a multi-party conversation as well. And we can either have a single task or the multitask setting. Either we can only solve the dialogue act classification task, or we can solve the dialogue act classification emotion recognition task together. And also you can have the some modalities, like either we can have the single modalities or the two modalities at a time, or all the three modalities. So we did a ablation study. Okay, so now we have, so you can see that individually, if you are considering the individual modalities, so text is giving us the highest F1 score. So with this multitask setting, we are getting 62.35% F1 score by using only text modality. Audio and video, individually they are not good. But when you are adding audio with the text, then we are getting 62.08. So there is a drop compared to the text. But if you are adding text plus video, there is a 6% increase. So individually text was giving us 62%, but when we are adding video with text, now we are getting 68%. So there is a 6% increase. So basically video is helping with the text. It basically is improving the text. And now when we are adding the three modalities, there is again a drop. So you can see that these results indicate that audio signal is not at all helping. So this may be because we are using OpenSmile for extracting the feature vectors from the audio signal. So maybe the OpenSmile is already a pre-trained model, and maybe there is a domain mismatch. Maybe this IMOCAP and mailed are using some other vocabularies which are not used in OpenSmile. So that may be one of the reasons. So basically somehow the audio signal is not helping. And also results indicate that yes, multitasking is better than the single task. So while by using the single task, we are getting the highest result of 64.14, but now using the multitask, we are getting 68. So 4% improvement. And then we have also done, like, suppose if you are not using the emotion recognition as one auxiliary task, but if you consider the emotion features as some additional features, then what is the performance? So in that case, we are getting only 60% F1 score. So these are some, utterances, like you can see, she is Larry's girl. So here the two level is disagreement. Multitask is also giving a disagreement, but single task was giving us a statement. So you can see for these examples, somehow the multitask models are correctly predicting the actual output. And this is also a kind of a heat map. you can see that when you are using only a dialogue act classification, focus is given or more on the words yes, yes, oh, yes, yes, I am, you can't stop me. So here the more focus is given or the more attention were put on the words yes, yes. But if you are solving a multitask problem, emotion recognition plus dialogue act classification together, then the focus is given on the can't, these words. So, and also this is an ablation study of different attentions. So what is the utility of using different attention, self-attention, intermodal attention, inter-task attention? So you can see that, only video plus text with all the attentions outperform the individual attentions. Yeah, so I think I should stop now. So any question from this portion? So I can take it now. Otherwise, we can take a break and yes. And then maybe we can discuss the other components of the dialogue systems like intent, slot, and dialogue manager, natural language generation. Maybe after the break. Students, if you have any question, you can ask me. Then should we take a break?